Hello everyone. In this video we are going to talk about the Lyapunov Stability Criterion, or some people call it second method of Lyapunov, or stability in the sense of Lyapunov. So this is one of the most important tools we have in analyzing nonlinear systems, the dynamics of nonlinear systems and their stability, which is developed by Alexander Mikhailovich Lyapunov in 1892. So what is it? So it says, if we have a nonlinear system with ODE in first order, x dot equal f of x, where x is the state of the system, then the equilibrium point of the system x equal x star is, first of all, is the point that f, the right-hand side, or the forcing function you might call it, becomes 0, okay? If x dot equals f of x becomes 0, then that means x dot is going to be 0, and when x dot is 0, that means x is not going to change. So it's going to stay there, and that's why we call it equilibrium, okay? So where f of x is 0, that's the equilibrium, okay? Yeah? So x stays at x star for any t bigger than t0, and t0 when the system reaches x star. So for any time after that, the system stays there. Now, one thing is to determine the equilibrium point of the system. The second one is whether this equilibrium point is stable or not. So first, let's look at the example here that I have for you, the nonlinear pendulum with no external torque, but a viscous friction here at this point O. So let's say here, basically, you have a damper term, which is like b theta dot in the opposite direction to the motion. And as I said, no torque. And so here, let me move this theta up there. The mass is concentrated at the end, the length is L. You know, if you write the equation of motion about point O, sum of the torque about point O, which is this, is going to be equal to I about point O times theta double dot, or alpha. And sum of the torque here, the only torques that you have is this guy, negative b theta dot, plus this mg here. As you can see, the moment of, or the torque of this mg about point O is clearly clockwise, while the rotation is counterclockwise. And for that reason, it's negative, and this distance here is basically L sine theta, right? So negative mgl sine theta is the moment from what? From the weight, which you can see here. Now, I about point O, since it's a concentrated mass, is ml squared. So if you write it and simplify, this is your governing equation. Now, this governing equation is second order. What we have for Lyapunov, it's not about Lyapunov. Determining the equilibrium point for a nonlinear system has nothing to do with Lyapunov. Lyapunov starts here when it talks about the stability. So if we want to find the equilibrium points for a pendulum, the first thing is we have to convert the second order OD into first order. So we use our dummy variables, x1 equal theta, x2 equals theta dot, and x here, vector x is x1, x2. So vector x dot, which is shown by bold font, is going to be x1 dot and x2 dot. Seems like I have a typo here. And x1 dot is clearly equal x2, and x2 dot equals negative g over L sine theta, which is x1, and negative b times theta dot, which is x2, and of course divided by their own components, ml squared and L. Okay, so these are now what? Your first order ODEs. You have two of them. And so this bracket here, this matrix, this vector you might call, is your f of x, right? Now this f of x has to be equal to 0, and the correct notation is I show this f with bold font too, because it has more than one component. And if that is 0, that means both components have to be 0. So x2 has to be 0, or the velocity, the angular velocity, and the bottom term has to be 0. Now when x2 is 0, the top term, this term also becomes 0, so the only term down here is negative g over sine should be 0. G over L is constant, so sine is 0. And for what angle sine is 0, it has to be either 0 or pi. So the equilibrium is what? The equilibrium when the angle is 0 or pi, and when the speed is 0, and you know that basically corresponds to what? Pendulum being down here, or pendulum being what? Up there, correct? So this is where theta is pi, and down here is when theta equals 0. So if we keep the pendulum at the very top point or the bottom point and keep it stationary, right? If you can, very, very carefully leave it. The bottom one is easy, but the top one, it has to be perfectly upright. Then it is in an equilibrium point, and ideally, if nothing pushes this top one, it's gonna stay. But you know, it's very hard to keep it upright. So it seems like this one is stable, that one is unstable, and by stability I mean if I give the system a disturbance, if I move it a little bit from this 0 position, right? If I lift it up a little bit, then it goes back to where it was, right? You know, if you give it something, then ultimately it comes back here and stops. The reason for stopping is this damping term. But for this one, if you give it a small disturbance from this upright position, not only it doesn't go back, actually moment by moment, this angle gets bigger and bigger, and you get away from the equilibrium point. So it seems like this top one is unstable and the bottom one is stable. Now, how do we show that using this Lyapunov method? Okay, so let's talk about that. So here it says this solution is, this equilibrium point is stable if and only if for any delta bigger than 0, there is an epsilon, a function of delta bigger than 0, such that if the initial state of the system is within a radius of delta from equilibrium, then the state of the system at any point will be within a radius of epsilon from the equilibrium. And here we assume that this x0 is equal 0 in this case. Otherwise, this norms has to be x of t0 minus x star. Okay, and here also this x star has to go inside the norm. So here when we say null solution means it's 0, but if it's not 0, the equilibrium point, then you have to bring it inside. So what does it mean physically? It means if I start within a delta radius of this equilibrium point here, which is x star, then, right, you see here I started my initial state inside the circle, then I can be assured that for any time after that time, the state of the system, which is basically any point on this trajectory, right, the state trajectory would be inside this circle with radius of epsilon and will never exit that. In other words, the state of the system will also always stay bounded and within some limits. Okay, yeah? So this is the stability in the sense of Lyapunov. Now we call it asymptotically stable if the x of t, instead of staying within a radius of a circle with radius epsilon, it goes to 0 when time goes to infinity. So what does that mean? It means I start here, but then over time, this guy what is gonna go to 0 and we end up at 0. Okay, so basically all of the energy of the system will be dissipated and the system is gonna stay there forever at 0. Yeah, so that is called asymptotic stability. So now we want to see, we have two equilibrium points now for the pendulum, which one is stable, which one is unstable, and if they are stable, are they just stable or asymptotically stable, huh? So we need to talk about that. Well, how do we do it? This epsilon delta method, okay, is not as convenient. And this showing that x of t goes to 0 requires that you have a solution for x of t. Most of the times these differential equations of nonlinear system, they don't have an analytic solution, so you cannot take a limit. Then you might say, well, I do simulations. Yes, but with simulations you cannot prove anything. Okay, because you might say under one simulation it worked, under another simulation, another different condition, it might not. You cannot exhaust all possible scenarios. Okay, so this epsilon delta, or this one, is not really something that we could use. So Lyapunov did this. He said, let a v of x be a continuous function with continuous first partial derivatives in the neighborhood of origin. And here we assume that origin is what? Your equilibrium point. If not, then we say in the neighborhood of your equilibrium. Then, and here this x, by the way, is your vector x, which is the state of the system. If this v function is a positive definite function, what does positive definite means? Means it's only zero. By the way, this v is a scalar function, okay? So you pass to it vector x, but this v itself is what? It's a scalar function. So here, this v function at a state of 0 at origin is 0, but anywhere else it's not equal to 0, and actually it's positive. Okay, then we call this v function a Lyapunov function candidate. Okay, that's not the stability criterion yet. This is just a definition right now. So if we can find a scalar function of states which is only 0 at 0 and anywhere else is bigger than 0, we call it a Lyapunov what? Candidate. For instance, if your system has, in this case, two states, x1 and x2, one such function will be what? Will be basically v of x equals x1 squared plus what? x2 squared, right? Or if you want to write it in a vector notation, you can say what? You can say x transpose times x, huh? So let's write it down. So you can write it this way. Clearly, only at origin, when x1 and x2 are 0, this is 0. Anywhere else, this is what? Bigger than 0. So this is what? This is a positive definite function, right? Okay. Now, let's talk about the Lyapunov stability. What does Lyapunov stability say? By the way, before I move on, this v function, which we call the Lyapunov candidate, sometimes we also call it the energy-like function. Why? I'll tell you. Wait a second, and I'll tell you why we call it a energy-like function. So let's talk about it. What does the stability method of Lyapunov say? It says the null solution f of x is stable if you can find a v of x positive definite such that the derivative of that v dot is negative semi-definite. Negative semi-definite means v dot of x is less than or equal 0. Now, if we find the derivative to be negative definite, which means v dot be what? Be only negative, then what? Then the system is asymptotically stable. So if v dot is negative only, then the system is asymptotically stable. If the system is what? If the derivative of v, this energy-like function, is negative or 0, then it's what? Then it is stable. And you can see why. Because this v, which is like the energy of the system, and it involves the state of the system, if this v is, the derivative of that is negative or 0, what does it mean? Means v is always going to go down, or at best stays constant. So if you plot v versus time, right, if you plot v versus time, it has to be a decreasing function, and at best in some areas it might stay constant like this, but it has to be something like that, right? And remember, this v is always positive, so it always stays above this x-axis. So what happens here? If you start at this point, at this x, right, and v is decreasing, because v is a decreasing function, that means the norm of x is going to decrease over time. So if you start within a big circle, over time you're going to go to smaller circles, or at best you stay on that circle, and that's when v is what? That's when v is staying constant. Now on the other hand, if v dot is negative, what happens? When v dot is negative, then v of x is going to go down all the time. And there is nowhere that v of x stays stationary and not moving. V of x is going to constantly go down, but it can never go to negative numbers. So ultimately, it has to what? Reach 0. And v becomes 0 means what? Means x becomes 0. Remember the definition of that, right? Here. Okay. Yeah. So it's only 0 when x is 0, so that means your x goes to 0, and x goes to 0, that's the definition of what? Asymptotic stability. So you see, it does make absolute sense, and that was, although very simple to learn, it's very meaningful and powerful. Now, a few things. One, although this method tells you under what condition your system is stable or not, or asymptotically stable, it does not give you a way to find this v function. Not always finding this v is a simple job, a piece of cake, okay? So most of the time it is, but not always if the equations of motion of the system is complicated. So this method does not give you any way to find v of x, but most of the time the energy of the system, the mechanical energy of the system, can be a good candidate, can be a good choice. That's why we call it what? Energy-like function. And why do we call it energy-like? Because sometimes we can find some functions which are not exactly the energy of the system, but they are similar to the energy of the system, and they still work with this theory, and they still prove that the system is stable or not. Yeah, so that's why we call them energy-like. And by the way, if v of x equals a constant c, we call that what? We call it a Lyapunov surface. So basically those constant levels of energy or energy-like in a system, we call them a Lyapunov surface. I'll show you when we go back to the Lyapunov, when we go back to the pendulum example. Okay, so one other thing we need to know is, well, let's say we define some v of x, okay, we improvise and we find some v of x, okay, or we use some energy function. How do we take the derivative? Well, it's very easy, because v is a function of x, right? Taking derivative of v is a chain rule. So we have to take derivative of v with respect to its parameters x, and then multiplied by the derivative of those x parameters or x states with respect to time. So it's going to be partial of v with respect to x times xi dot. Summation I goes from 1 to n. And where do we get these xi dots? From what? From these equations of motions. These xi dots are equal to their components of f of x, like here you see x1 dot is x2 and x2 dot is what? This function down here. So we get those x dot from equations of motion, this partials from the definition of v. We get this summation and calculate v dot, and then see whether it's negative or less than 0, or it's not. If it's not, then the system is unstable. Okay, now one last thing I say before we go back to our pendulum example and look at these equilibrium points. Just wanted to mention, this is called Lassalle's theorem, and it says that, let's say you found a Lyapunov function v such that v dot is negative semi-definite, like that. Then the null point is asymptotically stable. So see, last time we said that if v dot is negative or less than 0, and negative equal or less than 0, I'm sorry, then we say semi-negative. The system is just stable, not asymptotically stable. Now, the Saul says it could be asymptotically stable if v does not vanish along any solution of f of x equals 0 other than when x is equal to x0 or x star. Okay, yeah? So as long as this v does not disappear, yes, as long as this v doesn't become 0 for any x other than the solution, even if v dot is negative or equal 0, less than or equal 0, still the system is what? Asymptotically stable. Okay, so now let's go back and look at what? Look at the pendulum example. Remember, the equations for the pendulum are these two, right? The first order ODEs. Remember that we found two equilibrium points. Now we want to see which one is stable, which one is not. So here, we look at what? We look at a v function. So here, remember we said that the energy could be a good candidate. So let's look at this energy. Here, what is this energy function? This energy function is mgl 1 minus cosine theta plus 1/2 ml squared theta dot squared. What is this? Well, L squared or L theta dot, you know, that's the V, that's the velocity of the pendulum because it goes on a circle. So that's 1/2 mv squared, that's kinetic energy. And mgl 1 minus cosine theta is your potential energy. So that is P, that is K. So this total thing is your mechanical energy. That is your total mechanical energy of the system. And now, for theta, we plug in x1, and for theta dot, we plug in x2. Clearly, this function is always bigger than 0 if x is not equal to 0. And by x, I mean the total x vector. Now, if x vector is 0, which means x1 and x2 are both 0, 0, then this guy is 0, and cosine of 0 is 1, this guy is 0, so the whole thing becomes 0. So this function is only 0 when both x1 and x2 are 0. Other than that, it's always positive. Why positive? Well, this one is obvious. This is a quadratic term. This one, you know, cosine is always less than or equal 1. So 1 minus cosine is always positive as well for any x other than 0 or 2 pi, right? And 2 pi is the same as 0. So clearly, this is the case. Now, this is this v function, right, which is clearly positive definite function and positive for non-zero x. If we take derivative of that, v dot is going to be partial of v with respect to x1, x1 dot, partial of v with respect to x2, x2 dot, right? I'm using this formula here. Partial of v with respect to x1, clearly this constant, the other term negative mgl cosine is going to be positive mgl sine times x1 dot, and this one is going to be simply ml squared x2 times x2 dot. Now for x1 dot and x2 dot, I bring them from this top one here. So this is x1 dot, x2, and the x2 dot is this guy. So I'm going to replace them down here. You can see, right? So x1 dot is x2, and x2 dot is what? This term here. Now if you look, this term, when you simplify this term, the L and L goes, so it becomes negative mgl sine x1 times x2. And that is exactly the opposite of this term. So these two will go away with each other, will get cancelled. So the only term left is this multiplied by that, and ml squared will be simplified, so you get negative bx2 squared, which is, of course, always negative as long as x2 is not 0. So you see your v dot is negative, right, for any x other than 0, and your v is positive for any x other than 0. So clearly this system is what? asymptotically stable, and you know it is a pendulum with the damping. The energy of it will go down, down, down until there is no energy, and the system will what? Will stay at rest and stay there forever. Okay, so it becomes this scenario here, that x of t goes to 0 and ultimately settles down at 0, so the system is what? Asymptotically stable. Now, you might say, well, is it the system that is stable, or is it the equilibrium point? That's the equilibrium point. The system, stable or unstable, is not really that meaningful, because a nonlinear system has what? Has more than one equilibrium. A linear system only has one equilibrium point at 0, so that's fine. But a nonlinear system has different equilibrium points, and each one of them could be stable or unstable. Now, in this case, which one of these equilibriums, 0 or pi, which one of them was this case? Well, look at that. Here, this guy, remember, was 0 when what? When x1 becomes 0 or 2 pi. So this function is 0 for what? For x1 of 0 and x2 of 0. And that is your first equilibrium point. That's where your angle is 0 and your speed is 0. So this point here, this one down here, this guy is what? Stable and asymptotically stable. Now, what about that guy up there at pi? For pi, we need to change the function v. Why? Because this v function is not going to be 0 around pi, around theta of pi. So what should we do? Well, let's take a look again. So this time, my v has to be 0 at pi. So now, let's change this a little bit. So now I'm looking at this point, and you know cosine of pi is -1. So if I want this to be 0, I have to make this a positive. So cosine of pi is -1 plus 1, that becomes 0. Now this term is 0 at pi, and outside pi is positive. Okay, yeah? So if we change that to positive, what happens? This derivative here becomes negative. Yes? So that becomes negative. And this time, this negative and that negative would not cancel each other. So what happens? It's not just simply going to be negative bx squared. There is another term, and that term is what? Negative what? 2mgl x2 times sine of x1 minus bx2 squared. So it's going to be this. Now, can I make sure that this term here is always negative? Well, clearly this one is at x2 of around x2 of 0. What about this guy? If the x2 is not 0, right? So here, let's assume that for a moment, x2 is not equal to 0 and x1 is around pi. So we want to look what happens outside this point. We want to look at these areas here. Okay, what's happening? Can I guarantee this term to be also negative added to that? Well, that depends on what? It depends on x2 and it depends on sine of x1. When you're around pi, what happens to x1 or sine of x1 or sine of theta? Well, if you're less than pi, right? If x1 is less than pi or bigger than pi, then what happens? If it's less than pi, then clearly, let me write it somewhere with some more space. So if x1 is less than pi, your sine of x1 is positive. If it's bigger than pi, right, you go to the third quadrant, and now your sine becomes negative. So look at here. You see that? x1 sine of it is negative. And if x2 is positive, which means you're still going counterclockwise, so you're here basically, right? You're spinning this way, so x2 dot is still positive, but x1 sine of it is negative, then this whole term here actually becomes positive. And guess what? If this positive term dominates this negative term, the whole thing can be positive, because most of the time this damping is not such a huge term, but MGL could be, especially if there's a line pendulum. So this term can dominate that, and the whole term becomes positive, and when it becomes positive, that means the energy of the system can increase. And when it does, guess what? This guy is going to be unstable. Okay, do you see that? Yeah. So Lyapunov talks about the stability, but if you cannot show the stability, and you can show that there might be scenarios where the function becomes positive, v dot, then you're looking at being unstable. Now, one last thing is, does this method apply to linear systems? We know Lyapunov developed it really for nonlinear systems, because analysis of nonlinear system is very hard, right? But can we use it for linear systems? Yes. And you might say, well, linear systems, we can already look at what? If the system is x dot equal a of x, we can look at the eigenvalues of a and see if they have a negative or a positive component, right? A real negative component or positive real component. And look at that, yes. But can we use this method for it? Yes. The question is, what kind of v do we use? Well, v here, we can easily show that it could be x transpose px, where p is just a positive definite matrix, okay? And the question is, what is p? We can find p in this case. So in this case, we have a suggestion for p, for v, and we can find the parameter it needs. We can find this p matrix for it through what? By plugging it back into the equation, what happens? Well, what is v dot? If v is x transpose px, v dot is going to be what? Is going to be x dot transpose px plus x transpose px dot. Now, what is x dot? X dot is a times x. So it becomes what? If x dot is a times x, then x dot transpose is going to be x transpose a transpose, like that, times px, and plus x dot transpose p times ax. And if you look at these two, they both share x transpose x on their left and on the right side, so you can factor it out, and inside of it you will get a transpose p plus pa, which is this guy. So v dot becomes that. Now if this v dot is negative, right, then the system is stable, because p was positive, which means v is positive, right? Because this term is a quadratic term. So as long as p is a positive definite matrix, v is always positive for non-zero x. And if this v dot, we can find a positive definite matrix q such that this guy here becomes equal to negative q, which basically means v dot becomes negative x transpose times q times x, which is clearly negative because q is positive, then the system is stable, and it's asymptotically stable. So all we need is to find a matrix P such that this equation is valid. And the choice of Q is arbitrary, so as long as you plug in here any positive definite matrix Q, and you can go as simple as identity matrix, and solve for this unknown P, that is what you need to plug in into V and show stability. Now this equation here is what we call Lyapunov Algebraic Equation, and you can use it by hand, or you can, if the dimension of A is big, you can use this command in MATLAB called Lyap. If you pass to it A and Q, it does give you P. The only thing is A and Q, they have to be numerical things. So A cannot be symbolic. Okay, A has to be double numbers and Q 2, then it gives you a matrix P for it, and it solves for this. Now, if this A is symbolic, you can use symbolic solvers here, and you can also do it by hand. For instance, if we go back to the pendulum example, in the pendulum example, if I go ahead and basically assume that this angle theta is small, so I want to look at the linear pendulum. If this theta is small, then sine of x1 can be approximated by x1. So in this case, x1 dot equals x2, x2 dot equals negative g over lx1, negative b over ml squared x2, right? And you can write it down like this in linear format. Now this b can be b over ml squared, or we can just leave it as is. Okay, yeah? You can assume that ml squared is equal to 1. But if we want to add that, all we need to do is, wherever we see this b here, which I assume I see it here, and here, and here, you just divide it by ml squared, and that makes what? Now this whole thing to be multiplied by ml squared, and this one too. Now, of course, just the second term, not the first term. Like that. So here we multiply A transpose P plus P times A. Here we assume that it's a positive definite matrix, so it has 3 components, P11, P12. These two have to be the same, and then P22. We don't know these 3 components. We have to find them. For Q, as I said, I go with identity matrix, right? And this is A, and A transpose P plus PA equals negative Q. This guy here is A transpose P plus PA, and this is negative Q. And if you solve for it, you set this equal to that, right? These two are the same. So you get rid of negative, multiply by L divided by 2G. That is going to be your off-diagonal component. Once you know your off-diagonal, then you come here, you compare this one with this. Since you already know P12, you solve for it. Now you solve for P22, which is going to be this. And once you know P22, now you go to one of these off-diagonals, let's say this one, compare it against that. Now you have this one and this one. You solve for P11, which is going to be this. Okay, done. So as soon as you pick those numbers and plug in, you can get the system to be proven as a stable. Yeah? And again, if you know numbers, you can use the Lyap function to give you the P as solved solution. So hopefully you saw what is the Lyapunov stability and how to use it for a system like nonlinear pendulum to find the stability or instability of its equilibrium points and how we can possibly use it in a linear system. So thank you so much for your attention, and I'll see you in the next video. Thank you.